Good afternoon and welcome to Design Master Training. My name is David Robison. Today we are going to be looking at arc flash calculations. If you're attending the training live, you can ask questions in the chat box. If you're watching a recording of the training, you can call or email your questions. Our phone number is 866-516-9497 and our email address is support@designmaster.biz. So we're going to be looking at two things here. One is the arc flash calculations in general, just a little bit of an overview of how that works, and then also the specifics of how to do it in Design Master. I'm curious, what is your biggest struggle right now with arc flash calculations? Where do you have trouble, or where do you have problems with that? Let's go ahead and write in the chat what you're having trouble with today with arc flash calculations. Mary Beth says she's having trouble with her breaker curve time. Azim's having trouble with the time current curves. Yeah, definitely figure out those time current curves and the breaker time. That's a big deal. Aaron has trouble with the wire lengths. That's a huge portion of the calculation as well. Tim has trouble with getting fault information from the utility. Yes, getting actually other people to participate and getting their information is always a trouble. Brian, trouble with the gear and the labeling. Great, thank you. That will help me kind of guide the conversation here, make sure I get these questions answered as best I can, at least show you what I can do in our software. So arc flash has a fair number of moving pieces in it, some of it related to Design Master and some of it not. The first step with arc flash is that you do have to get your fault current figured out. Kind of an input into the calculation there is the fault values. So if you're using our software in Revit, that should be fairly straightforward because we're calculating that already. So I've got Revit pulled up here, and just kind of in the normal course of doing the work, we're going to calculate the fault for you. Fault is going to be a function of really two different values. It's going to be your feeder length and the wire size. And then there's a third one. And then there's also the starting fault. You need to get this calculation. You need to make sure this is all set right, obviously. The fault, the starting fault, you do need to get that from the utility. I don't know that I have any special insight in terms of getting the utility to talk to you about what the actual fault value there is. But you do need to get in touch with the utility and figure out what your starting fault is, because that's going to be the basis of this entire calculation. And it's important to get that value, because if you don't have that value, you're kind of starting from a guess, and that's not maybe the best place to be starting from. Then for the wire lengths, if you are modeling this in Revit and you're placing your devices in the project appropriately, Design Master is going to be calculating those wire lengths for you. So if we pull up the Design Master panel edit command, and we take the switchboard, for example, and you look at the feeder, the wire length is set here in this feeder section. So this is where Design Master is pulling that wire length. We have a couple different options for the calculations. We can do right angles, kind of an XYZ calculation. We can do a straight line where we do a straight line in the XY and then do the elevation difference. You can do the Revit calculated length where you do the circuit path in Revit, or you can type in a number. So all of these are essentially approximations of the length. This is where you have to come in as an engineer and decide if these approximations are going to be appropriate or not. As we're going through this, there's a lot of places where you're having to make some assumptions and best guesses to figure out what the answer is going to be. And so you could obviously, if it's built out, you can go out and you could trace the path if you have it. If they've got as-built, you can use that. But this will give you, if you've got the stuff modeled in Revit, at least something close that in general is going to give you a number that's fairly close in terms of what the fault's going to be. Just as long as you choose a calculation, if you're going underground, you're going to use a straight line. If you're in the side of the building, probably more the right angles are what you're going to use there. So that's where Design Master's pulling that length. We do our best with the information we have available to us. And those lengths are going to be important because the length is going to impact that fault value that you're going to get. The other portion to the fault is the wire size. This we at least do know based upon what you specified. So the software knows the size of the wires, and so we have the impedances associated with that. So that's actually a known value, and you can get that from your model in Design Master. You should be getting that anyway, so that kind of, you're getting that for free based upon using our software. You've got that available. And so that gets you your fault value. And so once you then have the fault, then you can take the next step and do the arc flash calculations. So arc flash is defined by an IEEE standard. It's the IEEE 1584. They came out with a new version in 2018. Prior to that, they had a version that was from 2002. So this is really the document that has the calculations for the arc flash. They're not a cheap document, so most people haven't actually seen them directly because it's a couple $100s to actually purchase this 100-page book. You're paying for all of the research that went into creating this document because just pulling up the front page here, I've got a copy because we use it for our implementation. Who are the people who are working on this? It's a number of large industry, Cooper Busman, SKM gets involved, GE. So these people are all getting together. What they actually do is they were running experiments. They're like, okay, let's put together a panel, let's do an arc flash, and let's measure what the incident energy was on that flash. And so that's how they actually figured this out. It's basically empirically derived based upon running a bunch of experiments. And what they found, the 2002 was working fairly well, but then some people did some more experiments in preceding years, and they realized, there's some situations where that's not accounting for things properly. We've got some variables in there that don't actually matter. So 2018, they came out with a new version, and so we have the 2018 implemented. And this is the best understanding right now of how to calculate arc flash. I'd like to say, hey, this is going to be exactly right, but the reality is that arc flash, it's not as precise as you would like to think it should be. That, like I said, it's empirically derived. This is our best understanding. We had a best understanding 20 years ago that's now no longer the best. In 20 years, they'll probably come out with another update as they've run more experiments and gotten more stuff accounted for. There's a question in the chat. What is the approach for single phase? Oh, okay, yeah, sorry. As I read it, I understand the question. So our software is generally doing 3-phase bolted fault. And again, if you read the IEEE standards, generally in single phase, you're not going to have to worry about arc flash because it's unlikely that you can sustain an arc at some of those values. I'm trying to remember if the IEEE even addresses single phase or not, or if it's assuming a 3-phase system. Yeah, so again, this is where you actually, to really do this arc flash, you need to go take a look at what they did in the IEEE standard. And the model is for 208 volt to 15 kilovolts. So less than 208, the model doesn't work. And it's also for 3-phase, line to line. So that's what they did for their tests. They didn't actually run tests for single phase. There's another calculation, the Lee method, which is an older one that covers more stuff, but not as precisely. It overestimates the arc flash values. I'm trying to remember if that covers single phase or not. I'm 100% looking this up right now in my book. I'm not seeing where the boundaries for what the Lee method is. So the single phase, you kind of start getting, again, outside the range of what we even know in terms of arc flash. So that's the reality there. And for single phase, you're usually looking at smaller voltages where the assumption is you're not going to sustain an arc necessarily even there. So again, these are all based upon that IEEE standard. And so the standard, they ran a bunch of tests and they determined what values mattered and what values didn't. And so in Design Master, we've got this arc flash calculation section here. And this is where you input all of those values for the physical configuration of your panel. This is where, to do this right, you need to know what panel you're actually specifying. You need to know the actual dimensions of it. you can't just say, okay, at some level when you're doing your design, you're like, okay, panel, transformer, panel, and you're not necessarily thinking about the specific brand and sizing of the panel. That does come into play for Arc Flash. Arc Flash really requires you to know what's going to be installed. That said, knowing that a lot of our customers are engineers who don't necessarily even get to choose that, we have default values for everything where it says unknown. So it's specifically saying, I don't know this value. And in all of those cases, we will default to the value that gives you the highest Arc Flash value. So these are kind of worst case scenario numbers, so that if you don't know what it is, you can choose unknown, specifically calling out, I don't know what this is, and then knowing that the software is going to give you a high value based upon that. So for the values that it does care about, the first is Electrode configuration. And so there's 5 different options here. And for that, I'm going to switch over to my browser. And we actually have a page on our website that has a pretty little picture here that will show you what those Electrode configurations are, because we can describe them in words, but a picture is way more obvious. To get to this, if you ever want to, if you go to Support and Knowledge Base, click on that. You can search for Arc Flash, and this will pull up all of our Arc Flash documents here. We've got a bunch of resources that are available. The Electrode configurations is what we're looking at specifically. So you can have a box, and there's 3 where you've actually got an enclosure. Generally, for the building work that we are going to be doing in Revit, you've got some sort of enclosure. You've also got open air scenarios. That's if you're working on like the power lines and whatnot. So that's generally not what you're going to be working on. And then you've got whether the electrodes are vertical or horizontal. And for the vertical, whether they terminate in an insulating barrier inside the panel or not. So these 3 options here, the vertical terminating or the horizontal electrodes are what you're looking at for your options. If we go back to Revit, the unknown is horizontal conductors inside a box. So that's the example, the worst case. There's the question, what is the example of an insulating barrier? There's the question, okay, does it actually matter? We have another blog post that has the sensitivity of the calculation based upon the different values. So for the electrode configuration, we've got this graph here. Red is the incident energy, purple is the arcing current. So purple is the arcing current that you use to find your trip time. Red's the actual final value. And this is for we just kind of took an example. It's a 480 volt panel, and we ran the calc just changing this value. And you can see that in the open air, the red, the incident energy, which is the final number you care about, is significantly lower. That's because you don't have the box essentially reflecting things around. So actually out in the open air is a little safer. These 3 on the left are with the box. The horizontal is the highest, and then the vertical, if you have that insulating barrier, it's a little bit higher than if you don't. So that would be a case where if you're uncertain, the insulating barrier is the safer option to choose because that's going to give you a higher value. So that can drive what your choice is if you're uncertain, you can go with the option that's going to be the more conservative value. And it varies a little bit from well, I don't know what these units are, but it's 2 to 3.5. Is the difference between the 2 vertical versus the horizontal option. So there's a doubling there in terms of the choice that you make. So that's for the electrode configuration. The next option is enclosure size. You only get this option if you say it specifically has an enclosure. So we'll go ahead and do that. We'll say we're vertical with the insulating barrier. Now we have the enclosure size. Again, we have a default value, which is 20 by 20 by 9 inches. Turns out that if you make the box smaller, that it doesn't have space really for the whole reaction to it kind of contains the whole thing, and it makes the actual final value smaller. Up to about 20 inches. You get to 20 inches, that is the optimum size if you want to maximize an arc flash. About 20 inches, it's not so small that it's constricting it, but it's still close enough that you get the reflections and everything else that it contains space. Past 20 inches, you start to approach the open air solution. So there's a local maximum at 20 inches of the maximum value for your arc flash. And then depth is a little bit weird, where there's really two values. You can put in a specific value and enter it in the software, but it's less than 8 inches and greater than 8 inches are the only values that actually end up mattering in the calculation. That's the way they break it out. So we have those two options, greater than 8 inches or less than 8 inches, kind of a shallow box versus a typical. You can type in your specific, but it ends up essentially choosing one of those two options based upon the number you type in. So you need to know the size of your enclosure. Going back to our sensitivity analysis, you end up with this graph here. And here, the red is for a typical depth where it's greater than 8 inches. And the purple is for less than 8 inches. And the enclosure dimensions, I believe it's the sum or possibly the largest. But at 20 inches, again, we've got this maximum. If you have a shallow depth, as your box gets smaller, the incident energy starts dropping. For typical depth greater than 8 inches, it ends up not mattering. It's, if you got an 8-inch or deeper enclosure, 10 to 20 inches, it's all exactly the same in terms of the calculation. It gives you the same value. Past 20 inches, it starts dropping off. But you'll notice it's not actually a huge drop off. We're up here right about 2, and then it drops off at a 50-inch enclosure to 1.5. So there's a 75% of the values there. So there is a drop, but it's not a huge drop. So this is one of the places where, again, if you don't necessarily know exactly which panel you're going in, if you use our default unknown values, you'll get a maximum, but it's not going to have a huge impact on the calculation. The next option is the gap between the conductors. And this is where you've actually got the conductors coming into the panel, how wide they're spaced apart. This has a maximum for less than 600 volts. It's a 3-inch gap. For greater than 600 volts, it's a 10-inch gap is what the maximum ends up being, because there's kind of a different calculations based upon the different voltages that we've got built into the software. So you don't necessarily need to know that, but if you just want a maximum, we're choosing the maximum value there. So it's 3 inches or 10 inches, depending on the voltage that you're working with. Largely, you're probably going to be in the 3-inch because you're going to be less than 600 for what you're typically doing for the building designs. If you also know the value, you can do known, and then you can type in what that gap between the conductors is. Again, looking at the sensitivity analysis for the gap between the conductors, the purple is the arcing current, and then red is the incident energy. So red is the actual final value that you are calculating. The purple is kind of the intermediate step. And what's interesting here is that with the gap between the conductors, you get a higher arcing current, but you get a lower incident energy, because essentially the arc, it's assumed it's going between the conductors, and so the arc isn't as long, so there's not as much energy being put out because it's just a shorter arc. So there's a bit of a balancing act there in terms of which ends up dominating. But as the gap between the conductors gets bigger, your arcing current actually goes down, but the incident energy ends up going up. So the larger the gap, the larger the final value ends up being. So as we'll look at when we look at the time current curves, the arcing current can have an impact as well in terms of how quickly it trips. So there's kind of multiple levels of things happening in terms of what's going to have the bigger value. Because if you cross a threshold on your time current curve, you can go from a 2-second arc to a single cycle arc. Then we've got working distance. This is how close the face of the technician is to the arc flash. So kind of the default generally is 18 inches would be what people would suggest is kind of the standard to use. We actually set our unknown a little more conservative. We're like, I don't know how close we're going to be. If you don't know, the software is going to say 12 inches, which is closer than the 18 you might typically use. Just saying, I don't know. And in that case, we're going to push the face up pretty close there. If you do know, you can type in known. You can put in 18 or whatever, however far away. Note that this will do the calculation at that distance. So this is you end up getting the arc and all of the incident energy, at the face and the body of the technician. His hands are going to be closer, so they're actually going to experience something more intense than what the rest of it is. So this whole calculation is so the guy doesn't die necessarily, but if you have to take that into account when you're speccing at the facility what gloves are required versus what the other requirements are, because the hands are going to be closer to the arc that's happening. In terms of the sensitivity analysis, working distance is a significant value. It's a inverse square, so the farther you get away, it starts falling off in an inverse curve. So the 12 to 18 actually is like a doubling, so that's a pretty significant difference. As you go from 18 out to 36 inches, again, it drops off, but not as quickly. But that distance does have a pretty good big impact on what the calculated value ends up being for that arc flash. And then the final is the arcing time. So all of those numbers, all of those settings that we just looked at, eventually you mix them up in the calculation, you run it through the IEEE 1584 standard, and you get two values. You get an arcing current maximum and an arcing current reduced. So the idea is that sometimes, even though the arc is shorter, depending on the trip time, it can end up burning if the arcing current is lower, it can actually take longer for the breaker to trip, and so you can have a higher incident energy. So you've got the two times that they recommend, okay, figure out the trip time for these two arcing currents. So these are what you take to your breaker curve to figure out your arcing time. So we'll look at breaker curves in just a moment once we've finished this out here. So for the arcing time, you can manually set the arcing time or have it set automatically by the software. If you don't have a breaker specified and you want it to be automatically calculated, we give you 2 seconds by default as the arcing time. The idea for that is that generally the person will get out of the way of the arc within those 2 seconds. So hopefully that ends up being the case, so that if it burns longer than that, they'll still get out of the way. And honestly, sustaining an arc longer than that is probably unlikely because your equipment will have melted at that point. So you've got probably larger issues if your arcs are going on longer than that. But hopefully the person gets out within 2 seconds, so we set that as the cutoff. If we don't have the curve, or you just want to enter the arcing times, you can manually set them, and you can just type in what those values are. And then also you can calculate them based upon the actual trip times of the breakers. So we'll look at the breakers in, again, just one moment. And then to finish this out, based upon that arcing time, that's where we calculate the incident energy. And so this is what you put on the label on the piece of equipment, which then drives the PPE that the electrician is going to be using. So we do the incident energy at the 2 different times, and we use the larger of those 2. In this case, they're both a 2-second arcing time, so the larger current is going to have the larger incident energy. Finally, we also calculate the arc flash boundary distance. This is how close you can be and be safe if you have no equipment on. So the idea is that you take this and you're supposed to mark out on the floor, and there's standards in the NFPA fire safety standards for how to do that. But this is the number that the distance you have to be away in order to not have your equipment on, your PPE. So we give you that value, and so that's how close you can be to only sustain mild burns in the case of an arc flash. And in terms of the sensitivity analysis, arcing time is a huge component. It's a direct, linear relationship. The longer the arc, the higher the incident energy. So the arcing time has a huge impact in terms of what the incident energy ends up being. So to find that arcing time, you have to know what breaker you're using. And this is where it does get a little bit tricky for engineers who are, if you're doing a design bid, you can say, well, it might be this breaker, but who knows what the contractor is going to actually end up using, because that's just kind of the workflow that we have. The contractor is going to be the one speccing and installing the specific breaker. You're going to recommend a brand, but you don't know what's actually going to be installed. So it's a little tricky at the engineer side to do this calculation appropriately when you don't know what your breakers are, because you have to know your breaker, and there is getting around that, but you're making some assumptions at that point. So if I come over here, I have pulled up a breaker curve for one of the breakers in my project. This is the time current curve, and just to familiarize everyone with this, at the bottom we have the current in amps, and then we've got the time in seconds over here in the vertical axis. And so it's telling you for a specific current how quickly that breaker is going to trip. Now, this looks really pretty, and it's got all sorts of good information. We previously said that we're going to cut off our calculation at 2 seconds. So when you're looking at this curve, as nice as it is, this line here is 2 seconds. Everything above that is not used for arc flash as we're doing it in our calculations. So this is the case where for that arcing current, it really only depends on where this intersection is here. So scrolling down, this is 1,000 amps. So this is probably about 2,000. So right at 1,500 amps, we go from a 2-second arc, because it's just never going to it's going to trip in like 10 or 100 seconds, to there's a little bit of a curve here where you've got some difference, but pretty quickly it just becomes a single cycle. The breaker is going to trip in that single cycle. If you don't know anything about the breakers, there's 2 ways you can go. You can just put everything at 2 seconds, which is going to give worst case scenarios. It's not necessarily the best, but that'll be safe. But it's going to require a lot of PPE for everybody. The other is that in the 10 to 20 times the breaker rating is where this instantaneous curve ends up. So this is a 100 amp breaker, and it's 1,500 amps is where we've got this instantaneous value. So again, between 10 and 20 times is where you transition from 2 seconds to a single cycle. So that's where you could take a look at what that arcing current is and manually put in a value, not knowing anything about the breaker, just guessing that, okay, if it's more than 20 times, it's probably going to trip in a cycle. If it's less than 20, to less than 10 to 20, you're going to have to think about that a little bit. Less than 10, it's probably going to take 2 seconds to trip. So if I happen to pull up this breaker, it has an arcing time of 1,800 to 2,000. So it's actually got 2,000 amps. And this is a 100 amp breaker. Yeah. So that's more than 20 times. So without knowing anything about the curve, we could just guess that that's going to be a single cycle, 0.167 seconds. And so you could manually set that. But to really do this right, you do want to go figure out what your breakers are and get the curves input. To set these curves, just so you know where these are set, they're set in the panel edit. In the question, there is a question of which curve you're actually going to use. So we're looking at panel LP1 here, and it has a main breaker on the panel. It's also got this upstream breaker. And for the arc flash, Design Master actually looks upstream of the panel for the first breaker, because the idea is that if you get the arc happening above this main breaker, if it's happening somewhere at the lugs or somewhere up above there, this breaker is not going to see it. So it doesn't matter if this breaker is going to trip, because it's just not involved. So you actually have to look at the breaker upstream in the panel above it, because that's the one that's going to trip, that's providing the protection for this fault in this arc flash. So if we run the panel edit and we select this panel, we've got the main disconnect and we can set the breaker curve there. But in this specific instance, that's not the one we're interested in. It's actually the OCP trip, the overcurrent protection trip. That's where that breaker is going to come into play. So it's this breaker curve here that we specifically care about. And here we can choose, run the select breaker curve, press that button. And here you've got the list of breakers that Design Master has loaded in. It's not a complete list, but it's expanding. If you have a breaker that you need to get added, send us an email and we'll get it added to the software for you. So we're slowly building this out, but we've got a pretty good list right now. So right now we're just looking at a Siemens breaker. And if I go back to that curve, like we said, the instantaneous is about 1500 amps for the maximum value there. And this curve, this breaker happens to have instantaneous options. So it actually has a setting on the breaker where you can adjust that. So if we ramp it back down to the low setting, it'll pull that in. So here, that's going to have actually an impact on this calculation, because now, you've got this whole range here where you've got something between the 2 and the single cycle where you've got a different time value. But again, they're all, they're not a single cycle, but they're also all pretty short times before you get up to, once you get past the instantaneous, it ends up being pretty close to just being a single cycle. But we will, if you've got 2000 amps, which is, the case here, we'll figure out what this value is here for the arcing time, and then use that to drive the calculation. And if I pull up this panel, you can see here that we've actually got 2 numbers that are within that range of that curve. So we have the different arcing times. So we've got different currents, and the shorter current has the longer arcing time. And in this case, they end up being pretty similar. It's slightly larger for that reduced current. So it's got this lower current, but has a longer arcing time. So it's going to have a higher incident energy there. And you'll see that with these lower arcing times, previously, I don't know if you noticed, the boundary with the 2-second arcing time was at 8 feet. With this lower arcing time that's past the instantaneous trip, it's 8 inches. So this is a much safer scenario here. We've got other options within the curves. So this is a thermal curve. We also have electronic curves. And again, all of these settings are dependent upon the specific curve that you're using. But if I grab one of these Eaton curves, this is an electronic curve, and then we've got all of the long time, short time, delay, and pickup values. So we can just choose all the selected values there. And so this is what this curve looks like with all of those, and then you can adjust it based on the actual settings. And then typically you'll be adjusting these for coordination purposes, and then the arc flash just depends on what's been selected. Make some adjustments, and you get a different looking curve. So we output a schedule. This is where we list for each device the incident energy at that device, and then the working distance, and the incident energy and the arc flash boundary. So those are the 2 kind of real outputs. So we have a schedule that gives you those values. And then really the final step is that you print a sticker and you put it actually on the panel so that the electrician has that, so that when they go to work on it, they know what equipment to wear. So to get those from Design Master, you run the arc flash stickers command, and you choose your panel, choose that LP1 we're looking at. And I'm actually going to choose a couple just to show you how this looks. And then you can print the stickers, and it will create these as an HTML document, which it then opens up in your web browser. They are put together nicely so that they will print 4 to a page on an 8.5 by 11. So you could take this, print, throw some sticker paper in the printer, and you could run this through your printer. You'll get 4 to a page. You have to cut them out, and then you can actually affix these to your panels. There are label makers out there. If you do run into a situation where you are needing to use that and you have a label maker, contact us and we can get these formatted to look nice with your label maker. We haven't gotten a whole lot of requests for that, so we haven't implemented it, but we can do that if that comes into play. And so for the output, we have these arc flash stickers. There's, just to walk you through why this is formatted the way it is. The first question is what goes at the top, warning or danger? There's standards for how labels should look. Danger is for something that's essentially always dangerous. Warning is for something that could be dangerous. And since arc flashes are rare, they belong as a warning rather than a danger. So that's why it's a warning. So we always have them listed as a warning in our software. We list the equipment and the voltage and the fault. Then for the arc flash protection, we list our working distance assumption and the incident energy. We do not list the PPE on the sticker. That is intentional. The NFPA, they've gone through various changes, and they currently recommend that you not do that. So you just list the incident energy, and then the facility needs to have some sort of document that says, okay, for this incident energy, here's the stuff that at our facility you actually wear in that case. So they take this back to their book, and then they go, or their sheet on the wall, and then they put on the appropriate stuff based upon what they actually have. So that's the actual workflow the electrician is going to use in the field. They look up the incident energy that you're providing on the sticker, go match that to the vests and the coats and the gloves that actually exist in their facility, or that they've got in their truck or whatever that is. We list the arc flash boundary, and then that should be marked out as well. We also list the shock protection boundaries, and that's just based upon the voltage. And then we also list the date so that there's some documentation of when this calculation was made. We don't list anything about you as the engineer or us as the software. It's actually recommended you don't list any of that stuff, because the idea with these stickers is to provide only necessary information. And while we would like to have our name and lights, it doesn't belong there. So we don't put it there. That needs to be documented somewhere else separately, not actually on the panel itself. When you're going to put on your incident, when the electrician's there, he doesn't care about you or me at that point. He just needs to know what that incident energy is to keep him safe. A lot of the questions are, what do you do when you don't know something? And the answer is, do your best to figure it out. You want to actually know. For the arc flash, you really need to know what's going in, what's actually being installed. That's important, and some of these calculations just really depend on that. If you don't know the values, figure out what some sort of worst case is, and then input that and use that as your assumption. There's a question, how do you address calculations through a transfer switch when supplied by a standby generator? That is a really good question, and our software does not handle that scenario very well. Essentially, to do that with our software, you have to disconnect the utility, so you have just the generator, and then run the calculation, and then reconnect it. It's not a great workflow, but you can do it that way. So you kind of have to manually make the connections to do the calculations. This is a place where something like SKM or Easy Power actually does a better job than we do at this point. So if you're doing those calculations and you need the arc flash in utility mode and in generator mode, you have to jump through a little bit of hoops there. We calculate the fault in both, but then we always use the larger fault. But as we were seeing, the larger fault ends up being a larger arcing current, and the larger arcing current is not always the larger incident energy. Our breaker database, we're filling it in based upon requests. We're kind of filling it in with current breakers that are actually actively being manufactured. If you're ever asked to go do existing work, which a lot of times you're updating something, you can end up in cases where you've got breakers that are 50, 60 years old. They might not necessarily be in our breaker database. You can contact us, and we can usually track those down. The manufacturers actually do have those breaker curves still. You just have to ask them, and they'll send you, the scanned PDF of the curve from 50 years ago. And then we can digitize that and get that in the software. When you're trying to match your breakers, if it's an existing situation, pictures of the breaker are always really helpful because you never know which settings on the breaker are going to have an influence on the curve. Because the curves, they do the curve, and they'll have one curve that'll cover like 10 different breakers, but there's one setting that matters. So if you're doing field work, do your best to get as many pictures of those breakers as you can, so that when you're trying to look them up, you have the information available. Thank you for watching today's Design Master training. Contact us with questions or comments by calling 866-516-9497 or emailing support@designmaster.biz.